Okay, so now we're ready to talk about the things that we can do with ethers. As we mentioned earlier, because they're aprotic, ethers are great solvents, right? They're generally unreactive, and so they're not going to mess up your reaction. So consequently, the reactions that we have with ethers are a little bit, well, thin, right? We don't have a lot of them. But we do have some that are going to, I think, look familiar. So let's look at these. Consider this ether below. Where are the most reactive sites? So when we ask a question like this, we have to ask ourselves, where's the activity likely to show up? Okay, so let's think about this. Is this reactive? No, that's just a methyl group, very polar. Non-polar, right? What about this one? What do you have here? It's just a CH2, right? Okay, this is a little more polar though because it's right next to an oxygen, right? And there's a polar bond here. So we have a little bit of a dipole, not big. Is it reactive? Yes, actually, it can be reactive, but anyway, it's not. I wouldn't say it's as reactive as this guy. Oop, that's partial positive. Sorry about that. Here's a partial minus, right? And that's an oxygen. It's got two lone pairs of electrons. See what I'm doing? I'm looking at the structure where the electrons are. I'm always asking the same questions. Shape and polarity. These are the two questions which help me dictate whether something's going to be reactive or not. All right, what about this carbon? Well, it's partially positive, right, because it's next to an oxygen, but it's more crowded than this one. So if we were ranking these in terms of their reactivity, I would say this is probably the most reactive site, then this one, and then this one. Can you see that these are just a bunch of CH2s, which are nonpolar? CH2, CH2. Can you see that? Okay. So here's my three reactive sites. It's an excellent exercise. Okay. Now, is this most likely to react as an acid, a base, a nucleophile, or what, right? Well, if this is the most reactive site, we've got a couple electrons. If this is the most reactive site, we've got a couple electrons, which looks like a nucleophile. Agreed? Okay. And nucleophiles, you know, there's a lot of overlap between nucleophiles and bases. So I'd say, yeah, probably a nucleophile or a base. All right, so let's consider acid-promoted cleavage. This is funny. This is a funny word. Acid-promoted cleavage. All right. So first of all, sure enough, look at that. We have what is acting as a base, right? Which turns out to be like a nucleophile. Okay. These electrons come and attack that hydrogen, and this is in an acid, a hydrohalic acid. When that happens, these electrons go off with the halide, okay, and so we're left with this halide, okay. Now that we have that, we have a decent leaving group. What's the name of this leaving group? Stop what you're doing right now, look at that and say it out loud. The name of that leaving group is methanol, right? Can you see it? So then we have an alkyl halide which is coming in, boom, and kicking off the leaving group. All right, so this is an SN2 reaction. You've seen it many times before. All right, now if we have extra acid, if we have lots of acid, then what will happen is this alcohol will do it again, right? So this was an ether, right? You see that? This is an alcohol. Okay? This will come in and do it again. All right, and so we get boom, and the leaving group leaves, water. Okay? So we end up with two equivalents of methyl halide. All right. You should practice that mechanism. That's going to be great review from Organic 1. It's also Organic 2. There's about 3 things you'll get from that if you practice that mechanism. Okay, draw a complete mechanism and predict the products for the following acid-promoted cleavage. Pause the video here and write this out, and then compare it as I do it. Okay, let me suppose you paused the video. Hopefully you did. This says XSHX. Okay, so we have plenty of this around. Boom. And boom. What's the name of this step right here? Taylor said this in class the other day. This is proton transfer, right? So then we've got, I'll try to go slow so my stuff is a little neater. Right? If you don't have that positive charge on your structure, you're missing out. Actually, it's going to be wrong. But more importantly, you're missing out. There's a nice important sticker to tell us what's going to happen. So you see a leaving group here now? What's the name of this leaving group? Okay, it's an alcohol, right? Okay, now that we've got that, oh, we have another leaving group here too. Right? Now that we've got that, one of these can leave, but in order for it to leave, we're going to have to push it, right? Because we'll have primary alcohol. We're going to have to push it. So this is either going to attack this side, boom, or this side, boom, right? Which is it? It's not this one, because you can't get in there. See how crowded that is? Okay, so it is this one. Now I'm afraid I boogered this up a good bit. Let me come back and go back to red, pretend like I've got a structure over here. Neatening this up a little bit. Am I doing better? There to there, right? Okay. If you're feeling like you're not understanding this or you're getting this wrong, you should pause the video here and draw out the product of what I have. Draw that out. Okay. Okay, that's the product of that. Tell me, what's the name of this? Name this and name this. This is an out. You can't, I say name. You might be thinking I'm looking for something specific. It's got to be general because we don't know what R is, right? But you do know the name of this. What is the name? Say it out loud. It's phenol. All right. I hope you don't feel goofy saying this stuff out loud when you're sitting someplace watching this video. But it is better for you to do that, and I ask you to put aside any feelings of goofiness or whatever, and just do it, because it's going to help you if you do. All right, so that's phenol. So really the purpose of this question is to ask you, do you think that we're going to get another elimination here? And the answer is no, we're not, because this is an impossible attack, right? Can you see why that's impossible? Okay, let's move on. So to promote cleavage, hydroiodic acid and hydrobromic acid, HBr, are generally effective. HCl is less effective. HCl is less effective, and HF does not cause significant cleavage. Why is that? Explain the trend above, considering the relative strength of the halide nucleophiles. Oh, there's a hint. Considering the relative strength of the halide nucleophiles. This is excellent review, folks. I'm honestly very happy that Klein put these questions in here. Explain the trend above, considering the relative. You do that, and come back and check with me if you like. So why is the cleavage considered acid promoted? Why did I say in the beginning that was a funny word rather than acid catalyzed? Okay, I'm going to ask you to go back also and look at that. Okay, why is it considered acid promoted rather than acid catalyzed? Good question. It's not actually acid catalyzed. And I've called acid catalyzed from time to time. I do. I hear myself do it. And it's wrong. Why? Why is that wrong? Okay, and then finally, practice. I say finally, we've got another couple slides here. Practice with the conceptual checkpoint 14.11. Okay. All right, so here's another practice problem. Predict the products for the reaction below and draw a complete mechanism. Pause the video, and then I will do it in front of you, and you can compare yours to mine. Excellent practice. Pause the video. Okay, I'm going to suppose you paused it, and I'm going to draw a mechanism, full mechanism. Okay, so watch what happens here. Remember we said these were the most reactive? Sure enough. Boom. Boom. I'm going to try to be careful with my space here. I'm going to try to draw real neatly. Very patient. Be patient. Patient, patient, patient. So I don't lose anything on accident, okay? Now, the previous slide said that bromide, watch this, the previous slide said that this is effective in promoting cleavage, okay? Because bromide's a good nucleophile, which was sort of the hint right here, okay? Bromide's the good nucleophile. So what's going to happen? Well, this is going to go in. Here's where yours may deviate from mine. May wrongly deviate from mine, okay? This is going to go in. This is a primary position, and this is secondary. So it's going to hit the primary first. Boom. Boom, right? You see that? Okay, trying to save some space here. Okay. And what I didn't say was that there was excess here. Excess HBr. Should have said that. Okay, if it's excess, and you should, excess HBr. Should have said that, okay? So if it's excess HBr, then we get another round, all right? Excellent leaving group. Wow, nice. The bromide comes in. Boom. And boom. Okay, now this is where it's important. There's a little subtle detail here. Oh, you know what? It's not even stereogenic, right? So it doesn't matter, but you really should draw that because it's inversion of configuration, right? Plus H2O. Okay, do you see that? Inversion of configuration? Okay, hopefully that's helpful. Okay, there's another reaction here that has to do, well, let's look at it. Okay, so the other reaction is, this is sort of interesting. This I do not, I've actually never had this on a quiz or exam, peroxides. I may do someday, so don't ignore it. I'm trying to incorporate more valuable details because I think it helps students appreciate what's going on more, and frankly, the context makes it easier to learn. Even though there's more details, context just helps. So I may have this on a quiz or exam someday. I never have. But let's look at it. You may have heard that ethers are explosive. Why? Because when they have access to molecular oxygen, they make peroxides or a hydroperoxide. Look at that, and they can be. This is really actually the thing that's explosive right here. This is the bad thing. Boom. Right? Watch out. Okay, so laboratory samples of ethers must be frequently tested for the presence of hydroperoxides before they're used. Autooxidation occurs through a free radical mechanism. Check this out. Okay, so first of all, this is good practice for you because we do radical mechanisms, and I want you to see them more often than less. Okay, so do you recognize this? Right, that's just the ether from before. We have hydrogens all over the place, but we're looking at this particular hydrogen. With that particular hydrogen, you have some radical initiator, okay? And the radical initiator takes one electron from this bond and then the other electron stays here, right? That's the other electron. So that's a radical, okay? Why that one and not another one? Well, it has to do with resonance, but Klein doesn't talk about that here, and we can drop it, okay? So if you want to memorize it, it's that one there. It's the one right next to it. Okay, that said, now O2, which has some radical aspect to it, can come in and form a bond with that radical. You see that? So this is propagations, where you take two radicals or a radical and have radical in the end, right? That's what propagation is. So you have a radical here, and you have a radical here. That's why it's called propagation. Okay? And then after you get that radical, this radical comes and reacts with another ether. This is just the same thing we had before. Okay, diethyl ether. All right, and it makes your hydroperoxide. This is the explosive guy. Okay. All right, so termination, radical reactions always stop with terminations, of course. That's what termination means, right? And a termination is where you get a coupling of two different radicals. In this case, these two radicals are shown to make a bond here, right? That bond is formed from the... Have I pointed out, or did your Organic 1 professor point out, that when a radical is reacting, it's a single barbed arrow, right? Because we're showing the action of one electron. Most of the electron arrows we have are that. This is the action of two electrons. The action of one electron is drawn as a single barbed arrow. Okay? So, recall that the net reaction is the sum of the propagation steps. This is from, I don't remember, chapter 9 maybe, chapter 10. So, the two propagation steps are coupling and hydrogen abstraction. And so, look at that. That is the same thing as this guy over here, so we cross it off. That's the same thing as this guy over here, so we cross it off. So this plus this is the net reaction, where that is our ether, in this case, and oxygen makes a peroxide. All right. So hopefully that's hopefully that adds some nice color to the story of ethers.